In this video lecture, we'll present the topic. In this video lecture, we'll present the topic of convergence of Borel functions. The first definition, which was already briefly mentioned in chapter 5, is when there is convergence almost everywhere. So almost everywhere means we have a sequence of Borel functions, and we say that they converge to a certain function almost everywhere if the set of points in the sample space for which the convergence does not hold has measure 0. So that's what we mean by almost everywhere. So the set of points where Fn of omega actually converges to f of omega contains almost every point, in the sense that, well, the set of points that fail to have this property is a set of measure 0. Before we move on to examples, it's good to have a second definition so we can use the examples to compare them. So convergence in measure is different from convergence almost everywhere. It says two functions, they are very close, which means they are not further than epsilon, with except on a set of small measure. Okay, so this is for each fixed n. So the difference between this and almost everywhere convergence is that here we fix some n, we look at the measure of this set, and we just want to say that the measure of this set is small as we make n larger. And it is denoted by Fn converges in measure to mu like this. So let us see some examples. Here is the simple example of convergence that happens in measure and almost everywhere. Our space is just the interval 0, 1. This is our space, and the functions we are considering are functions that are like this. And as we make n larger and larger, this is just shrinking here. And we can see for every point that we fix, okay, for every omega that we fix, as we take n large enough, this region here will be so small that will not contain this point anymore. So for every point in this interval, this function fn, evaluated at that point, will eventually become 0, and then stay 0 after that. So we can conclude from this that fn of omega will converge to 0 unless, so there's only one exception here, the only exception is this point, unless omega equals 0. So it means the set of points omega with this property equals the open interval 0, 1. And this means convergence almost everywhere, because 0, 1 and 0, 1, the only difference here is this point 0, but the Lebesgue measure of the point 0 is 0. So the Lebesgue measure of this point 0 is 0. So this means exactly convergence almost everywhere. Yeah, so if we consider here the set where it does not converge, then this will be just the point 0, and the measure of this set is 0. So we have convergence almost everywhere. And, well, we also have convergence in measure. And we also have convergence in measure to the same function f. So what is f here? F is the function 0. So we have convergence to f. And how can we see that? Well, let's take some epsilon. We can assume epsilon is less than 1, because if epsilon is larger than 1, it is even easier. And so the set of omega such that fn of omega minus 0 is larger than 1, or any number bigger than 1, this is empty. Okay? So, which means epsilon larger than 1 is not very much fun. So it remains to consider when epsilon is between 0 and 1. And then we see, what is this set here? When epsilon is positive but less than 1, what is this set? The set of omega such that Fn of omega minus 0 is larger than 1. So why am I writing this Fn minus 0 here? Well, because F is 0. And let me go back one slide. This is the definition of convergence in measure. I'm looking at the point where this is larger than epsilon, and I'm taking the measure of this set. So we're looking at this set here, and we want to compute the measure of this set. And then you see, well, here we put epsilon. And what's the measure of this set? Well, what is this set? When is the difference larger than epsilon? Here is epsilon. Well, that's exactly on this little interval here. So this will be, this equals the measure, because this set here is just the set 0, 1 over n. And the measure of this set is 1 over n. And so that measure tends to 0 when n tends to infinity. And that's why we say it also converges in measure to 0.